Let's work a Gauss's law example where we have a solid conducting sphere of radius 2 meters and we place a charge of 32 pi coulombs on it. Those charges repel each other, so they'll be on the surface of the sphere and they will be uniformly distributed. That's how they're the farthest apart they can get. In part A, we're asked to find the charge density on the surface of this sphere. The symbol for that will be rho sub s because it's a surface charge density. And that charge density would be the total charge on the sphere Q over the surface area of the sphere, which is 4 pi a squared. We know the charge on the sphere is 32 pi coulombs and that the radius is 2 meters. So for part A, we get that the charge density on the surface of the sphere is 2 coulombs per meter squared. In part B, we're asked to find the electric flux density field everywhere. Since the sphere is conducting, there is no electric field intensity and hence no electric flux density field inside the sphere. So for R less than 2 meters, there is no electric flux density field. The electric flux will emanate from the charges and it will have a spherical symmetry because the charge is distributed spherically on the surface of our sphere. To match the symmetry, we will choose for our Gaussian surface a sphere. We will now apply Gauss's law over our Gaussian surface, and the integral of d dot ds over that surface will be the charge enclosed. And we know that the charge enclosed is 32 pi coulombs. From the spherical symmetry, our electric flux density field only has a component in the r direction, and it only depends on r. Since we've chosen a sphere for our Gaussian surface, the magnitude of the electric flux density field is constant on that sphere, so it can be moved to the left of the integral sign. The unit vector in the r direction dotted with ds will just give us the surface differential in the radial direction, the magnitude of the surface differential in the radial direction. The integral over the surface of a sphere of d sub sr is just the surface area of that sphere 4 pi r squared. Or you could write the form of our surface differential in the r direction and integrate it over the surface of the sphere, which would mean integrating theta from 0 to pi and phi from 0 to 2 pi. So we have dr times 4 pi r squared is equal to 32 pi coulombs. So 32 pi over 4 pi r squared is 8 over r squared. And when we put r in meters, we'll get coulombs per meter squared. So here is our electric flux density field everywhere. In part C, you're asked to find the electric flux density field at A+. That means just off the sphere, so that you're in the free space just beyond the charge on the sphere. So essentially you can get that value by plugging in for the radius, our radius of our sphere of 2 meters. And you get that the electric flux density field on the surface of the sphere is 2 coulombs per meter squared. Notice the electric flux density field just off the surface of the sphere is equal to the charge density on the surface of the sphere. This is a useful concept, but it's one that sometimes people have difficulty with. But it comes from that one-to-one correspondence between charge and flux. From every 1 coulomb of charge emanates 1 coulomb of flux. So if you have 2 coulombs per meter squared on the surface of a metal, emanating from that surface then should be 2 coulombs per meter squared of electric flux. Of course, if it's emanating from a sphere, it quickly spreads out and decreases by our factor of 1 over r squared.